Okay, let me say that again. Today you're going to continue our unit on simple harmonic motion. You are going to, because you're going to do a lab experiment to determine some characteristics of a new type of oscillator, specifically a simple pendulum. I have 3 types of pendulums here, even though you only see 2. This is a simple pendulum, or at least it's almost a simple pendulum. A simple pendulum is like an ideal mass spring oscillator. For an ideal pendulum, you have a point mass, meaning a mass where all the mass is concentrated in one single point, and it is connected to a lightweight string. Lightweight meaning the mass of the string is negligible. Okay, so that is what a simple pendulum is. Obviously, in reality, we can't have a point mass on the end of a string. Although there might be point masses in the universe, the electron, a lot of physicists think that the electron is actually just a point mass. There's actually no dimensions to it. There are some experimental ideas that indicate there might be some physical dimensions, some volumetric dimensions of an electron or a neutrino, but we don't have the capability of making measurements that small, and it might actually be impossible to, according to quantum mechanics. But anyway, we can't do simple pendulums, ideal simple pendulums, but we can make them close to ideal by just making the string long and then the mass round and small. Okay, so here's a simple pendulum, as simple as we can get. And if I swing it, it has a certain period, right? That's a simple pendulum. This right here is a physical pendulum, okay? Physical pendulum means a long or an extended object, an extended rigid object that rotates back and forth about some fixed axis. I can change the nature of this physical pendulum just by changing the location of the rotation axis on it, and I'll get a different period, right? But the same idea applies. I get a period for this physical pendulum. And the folks at home did not see the physical pendulum. So here's what I just talked about for the people at home. That's a physical pendulum. What's an example of a physical pendulum that many of you might have in your homes? You ever seen a grandfather clock? Anyone got a grandfather clock? It's literally a pendulum. You never seen a grandfather clock?
I don't have one.
Okay. But then the tall wooden ones, right, where they got the pendulum inside. Why does the pendulum swing back and forth? Because it's timed so that it has a period of usually 1 second, maybe 2 seconds if it's a really large one. And then the time is kept that way. Interestingly, if you got a real grandfather clock like the expensive ones, and you plug it, when you plug them in, you're not plugging it in to actually drive the pendulum motion. You're plugging it in to just turn on lights. The actual energy that goes into fighting the friction and the air resistance of the swinging pendulum and to get the clock hands to actually move is located inside. That's why they're tall, because you take heavy masses and you lift them up, and they kind of get wrapped up as you lift them, or you have to crank them depending on what type. And then you give them gravitational energy. You do work in order to give the masses gravitational energy, and then as the pendulum swings back and forth, the masses slowly lower over the period of weeks or months. It takes a long time for them to lower because they're just fighting a little bit of air resistance, a little bit of internal friction in the axle, the rotation axis, and then just the energy needed to actually turn the clock hands. So that's a physical pendulum. That's something that you will experience from a physics standpoint next year if you take AP Physics C, Kyle. Another type of pendulum is called a torsional pendulum. And if you guys remember, we talked about a guy named Henry Cavendish, very interesting scientist from the late 1800s who determined what the value of big G is through a very ingenious experiment that involved a torsional pendulum. He actually was able to measure the actual gravitational attraction between big lead spheres and smaller lead spheres. Now, you can't just put a big lead sphere next to another one and expect the gravitational attraction to cause them to come together. It's not going to happen. But, let me take a roll real quick because I forgot. You're supposed to remind me, Kyle. What's going on, man? Tatum, Kyle. Kurt, field trip. Antonio, Idalis. Quarantine. Okay. So a torsional pendulum is this. And you guys might have done this if you ever played on swings when you're kids and you twist yourself up in a swing and then just let it wrap around right? That's a torsional pendulum. Oh my gosh. So if I just spin that, you notice when it spins around, it actually creates not a restoring force, but a restoring torque, right? Forces that cause rotation are called torque. And so you get that. And the period, you have an oscillation there. It's going to go back and forth. An ideal torsional pendulum would keep swinging forever, but there's a lot of energy loss in this. But Cavendish was able to set up his experiment. So you had two giant lead spheres, two small lead spheres connected by a lightweight rigid rod that was hung right in the middle by a really thin piece of quartz wire that was suspended from the ceiling. And then the gravitational force actually caused attraction between the spheres, and then it would overstretch a little bit, and then it would move back because of the restoring torque, and it would rotate back and forth like that with a very long period. The period is, I think, minutes, maybe even over an hour. I'm not really sure. Very careful observations of that oscillation was what led Cavendish to determine what the value of big G was in the late 1800s, to within 1% of the value that we know today. So very ingenious experiment, involved pendulums, what we're studying now, but specifically a torsional pendulum. We won't deal with torsional pendulums in this class, at least mathematically, but again, that's one thing that we do deal with in AP Physics C when you take that next year. Where'd this? Oh, okay, it's there. Okay. So, pendulums is what we're going to talk about today. What you're actually going to investigate today. You're going to be doing a self-directed lab. You're going to do 3 experiments within the lab. You're going to have today about 10 minutes, 5 or 10 minutes today to start formulating your thoughts, plan of attack. And then tomorrow and Friday, you'll have all class period to work on it. The lab itself will be worth a major grade. It will be due Friday night. Okay. So if I was you, I would aim to have it done by the end of class on Friday. If you follow my tips, I'm going to give you some tips as to how there's going to be 3 experiments in the lab. 2 of them should be relatively quick. The third one is going to take some time. It's going to take some brain power. But I'm going to show you how I'm going to do a similar experiment here in class. It will only take 10, 15, 20 minutes maybe, where I'll do a very similar experiment but with a mass spring oscillator. So you'll just have to do the same thing but with a pendulum. Okay. It is going to be on Pivot Interactives. Let me actually just read this because I wrote this with very specific instructions for students at home. So for the next 3 days, you'll be doing a Pivot Interactives lab experiment to determine what factors affect the period of a pendulum. Remember when we were talking about mass spring oscillators, we were like, does the amplitude affect it? Does the mass affect it? Does the spring constant affect it? Right? What affects the period of a mass spring oscillator? Now you're going to ask questions about what affects the period of a pendulum. In order to do this lab, you'll need to use the process of linearization, which Mr. Graham will cover on Wednesday. That's today. Linearization we've done before. We only did it, I think, once, though, so far, and it's been a while. So I'm going to cover the process again. Technically, it's not a technically demanding process, right? The gist is that you determine the relationship between 2 physical quantities. If it's linear, good. That slope probably tells you something. If it's not linear, then it's going to be hard to get information from that graph unless you know some higher level mathematics. But even if you know higher level mathematics, the process of linearization generally makes things a lot easier and a lot faster. And this is applications. It has applications in engineering fields, in science, in physics, in chemistry, and biology, any science, and by extension, any engineering field. The process of linearization allows the scientist or the engineer to obtain useful information from the analysis of data just by finding the slope of a line. Okay. Technically, it's not that difficult. Conceptually, for students, it is kind of difficult. If you remember when we did this before, you might say, yeah, that was kind of tricky, right? So we're going to do it again. We're going to do it multiple times before the AP exam. Understand that on the AP exam, I can't guarantee it, but you are very likely to have an FRQ where you're going to have to linearize data. They're going to give you a table of data. You're going to have to plot it, recognize it's not linear. You're going to have to linearize it, and then come to some conclusions based on that linearization. Okay. All right. So in order to successfully complete today's lesson and tomorrow's and Friday's, watch and take notes as Mr. Graham reminds you how to linearize nonlinear data using a mass spring oscillator experiment as an example. And I'll tell you what I'm going to do with the mass spring oscillator. You're going to have to do almost an identical thing when it comes to the pendulum. Follow the steps to determine what factors determine the oscillation period of a simple pendulum. That's the whole idea. You'll need to conduct 3 separate experiments, and we'll need at least 5 data points and a graph for each experiment. I expect the data tables to be properly labeled. I expect the graph to have the proper axes. You're plotting the dependent variable where it goes and the independent variable where it goes. And you need at least 5 data points. The last Pivot Interactives lab, I had students put 2 or 3 data points. It's not enough. It's not enough. But Mr. Graham, that's 15 data points because we have to do 3. Yeah, you got 2.5 days to do this in class. It's not hard. The lab that I'm going to get 5 data points within less than 10 minutes. Okay. So 5 data points in reality is not that much. If you're an engineer, you're a scientist, and you're actually doing real work in the real world or for a university, you got to get way more than 5 data points. So you just need to get 5 for each experiment. I'd follow this suggestion if I were you. I suggest you do the mass and the release angle experiments first. They won't be the most time consuming. Then move on to the length experiment. That will be the most time consuming. Since you are determining what physical characteristics will affect the period of a pendulum, your independent axes for each graph should represent those specific characteristics, while the dependent axes should all represent the pendulum period. Right? You're seeing how certain things affect the period. Those certain things need to be on the horizontal axis. Those are what you have control over. If you have control over a variable, that's the input, right? If you're talking functions, that's the input. The output goes on the vertical axis, right? That's the thing that depends on the input. So the period on all 3 graphs should be on the vertical axis. The 3 things that you're going to do mass. Does the mass of the pendulum affect the period? You're going to do the release angle. Does the release angle of the pendulum affect the period? And you're going to do the length. Does the length of the pendulum affect the period? Those are the 3 things. Again, do the length one last. Do the other 2, it doesn't matter the order, but I would suggest doing the length one last because it's going to demand more brain power than the other 2. And you're probably going to have to linearize that one, Francisco. Okay. Why did I call you by your last name? That was weird. Okay, pay attention to the points awarded for each part of the lab. You must produce proper graphs and provide good explanations if you wish to get a good score on this lab. This is going to be a major grade. I remember the last couple labs that we've done on Pivot Interactive, some people just didn't do one of the graphs. They just didn't do it. As you'll see, there's going to be 9 parts to this lab. Each part is you get awarded 10 points. If you leave any part of it blank, you've lost 10 out of 90 points. That is more than a full grade. Okay. That's more than 10 percentage points, right? 10 points out of 90 is a bigger fraction than 10 points out of 100. So don't leave anything blank. And I am going to grade this thoroughly. So if you just try to BS your way through it, it's not going to work. It's not going to work. You are going to lose a lot of points. We're halfway there, guys. We're more than halfway there. The AP exam is in a few months. We got to start taking these labs more seriously. For those of you that did well in the other... Right. For those of you that did well on the last couple labs, just ignore what I just said. But yeah, pay attention to that as well. The lab is due Friday night. I would aim to have it done by the end of Friday in class. It will be a major grade. Please ask Mr. Graham if you have any questions. My Zoom meeting is open. I actually had an AP Physics 1 student at home join last period. Oh, and I have another one. I'm sorry, I didn't. I'm sorry, Idalius. I just saw you there. I'm just reading the instructions for the day. I haven't got to the nitty gritty yet, so you haven't missed much. Okay. Making progress on this lab for today, tomorrow, and Friday will count for your attendance if you're online, which doesn't apply to any of you. Okay. So when you click on Pivot Interactives here, the link, you'll have to log in. It's been a while. Your login is your email, unless you did something weird. I can look that up for you if you want. I can't look up your password, though, so hopefully you remember your password or you have it saved. When you open it up, this is what you'll see. So these videos show the motion of many different combinations of pendulum mass, length, and release angle. The set of videos will allow you to vary the mass of the pendulum. Pendulum bob, sometimes called the plumb bob. The length of the pendulum, the release angle. But not every combination is available, so if you want to do an experiment where you vary the mass, click the independent button next to mass on the selection panel. I'll show you what that looks like in a second. This will show you what length and release angles angles to use so you can try all the masses. Okay, so this is what each trial is going to look like. It's very easy to see the instant that the pendulum gets released because this is an electromagnet. It's an electromagnet setup. If you remember the monkey hunter problem that I had in the back, right, when you launched the projectile, it broke the circuit, which detached the magnetic attraction to the monkey. This is a similar setup. You got an electromagnet here that is attracting the ball. The instant he lifts his finger up, it's going to break the circuit. When you break the circuit, it turns off the magnetism and the ball will start to swing. And you can actually see it. Like if you hit play, just find about where it is. Right there. And then you can just back up frame by frame and find the moment that the contact is broken. Right there. And then you get out your timer. And then you reset your timer so that now whenever you start advancing the frame or you just hit play, it's measuring the time here will tell you exactly how much time has elapsed. So for one pendulum, one period, that would be back to right about there, right? So the period for that particular oscillation was 1.2583 seconds. This does have 2 full oscillations. So you can go 2 full oscillations, divide that time by 2 to get a more accurate value for your time, if you wish. You can get pretty accurate with just one, so I'm not going to hold you to that because it does take a while. Other measurement devices here. This is where you measure the length of the pendulum. It is in centimeters, so I would convert that to meters. So everything jives. And then you got a protractor. That's what you're going to use to measure the angle. Right? 0 degrees is straight down. The angles are measured from that. As you'll see, all the angles are pretty small because the physics of pendulums that have bigger release angles, bigger than about 15 degrees, are much more complicated. To describe those, you actually have to use infinite series. If you've done calculus, you know a little bit about infinite series. But yeah, the physics there gets quite a bit more complicated. That's something that we don't even touch in Physics C. But you will in college. So yeah. So those are the measurements you make. You measure the release angle here. You measure the length of the pendulum with this guy, you measure the time with that guy, and then if you're varying the mass, you just choose the mass. Now remember, like when you got the ideal gas law, if you want to understand the relationship with just say the number of moles and the temperature and the ideal gas law, you hold everything else constant. You hold everything else constant, vary one of those, see how the other one responds, and then you plot those two on a graph to see what their relationship is. So here we got 4 quantities. We got the mass, we got the length, we got the release angle, and we got the period. You don't want to vary all of those trial by trial. You don't want to vary all of those at once because it will be literally impossible for you to pick out what is affecting what. So let's say we want to see how the mass affects the period of a pendulum. Well, then I go to mass and I click on the independent. The release angle for this for varying the mass, I have a few choices for the release angle. So I might just pick one, pick E. If I'm varying the mass, I want to use the same release angle for all 5 trials for the mass period relationship. And then for the length, I only have one choice, so I just got to use that one choice. Okay. Same thing. If you want to vary the release angle, then you have one choice for the length. That just means that's how many videos. They didn't want to make a video for every single combination, right? So if you're going to vary the release angle, then you're going to hold the length constant and then say the mass constant. Okay, and then click load after you pick one, and then it'll load that particular setup, make your measurements, measure the period, plot those data. Okay. All right, so as you see, you got experiment 1, experiment 2, and experiment 3. You're going to have to do 3 experiments, 5 data points each, a graph on each one, and then you're going to have to linearize if necessary. If the relationship is nonlinear, then you must linearize because you want to use that linearization to come to a specific conclusion, or at least come to an interesting conclusion. If the data don't show a relationship, like let's say that I want to plot the height of the people in this classroom versus the temperature in Honduras, right? Do you think there's going to be a relationship between those quantities on a graph? It's not going to make a line that you can describe with a mathematical function, right? It's just not going to happen. So that's what we want to do. We want to see if varying these 3 things affects the period individually, right? That's why we got to do 3 different experiments. Again, save the length. Do the length for experiment 3. Do the mass, release angle, or release angle and mass. See if there's a relationship. If there is, describe it. If not, don't describe it. If it is a relationship and it's curved line, then you got to linearize. That's what I'm going to show you how to do now. I'm going to show you again how to linearize graphs, but not with this lab because that's your job. So what I'm going to do is collect some data for a mass spring oscillator and then use that data to show you how to linearize. Okay. So let me make sure that those folks at home can see. All right, so here I have a mass spring oscillator. Well, I have a spring on a hook, and then I'm going to attach some different masses to it. And so let's pretend that instead of a pendulum lab, this is a mass spring oscillator lab. And I'm going to see how the mass attached to that spring will affect the period. Okay. I will keep the same spring, so the spring constant won't change. The only thing I'm going to vary is mass. So now remember, we can have multiple columns here. You can add columns. We're going to have to add one for any graph we have to linearize, but let's not jump too far ahead. But what we are going to do is vary the mass, measure how that affects the period. So my first column, and I'm going to look at your data tables. I want to see all these boxes filled in with something. Okay, don't leave them blank. Don't leave them blank. That's not good science. So I'm going to vary the mass. The units I measure mass in are kilograms. The variable is n. And then I'm going to measure the period. The units that I measure the period in are seconds. The variable is capital T. All right? And then I'm going to collect my 5 data points. And notice how if you're focused, if you're methodical, if you're not being distracted by friends texting or other things, doing work from other classes, this doesn't take that long. Okay, I'm going to get all these 5 data points in just a few minutes. So I'll start with 50 grams. That's not 50 grams. I'm going to start with 50 grams. But I'm going to use kilograms because I know that newtons are kilograms times meters per second squared. I know joules are kilograms times meters squared per second squared. So I want to use kilograms, meters, and seconds. So what is 50 grams in kilograms? 0.05. If that did not immediately come to your brain, you are behind. Okay, you need to be able to convert grams to kilograms instantly at this point. And then I measure the period. Now, do you think I can get a very accurate measurement if I go start, stop? You think that was an accurate measurement? No. So the easiest way to measure the period of something that oscillates pretty quickly is to do 10 oscillations. And then why 10? Because it's a pretty big number, and it's easy to divide the total time by 10. Right, so I just hit start. 1, 2, 3, 4, 6, 7, 8, 9, 10. 5.29 seconds. So the period is that divided by 10, 0.529. Next data point. Let's hang 40 more grams. So each one of these guys is 20. So I'm going to hang 40 grams. So this is 90 grams now. So how many kilograms is 90 grams? 0.09. And measure the period. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7.18 or 0.718 for one oscillation. All right, let's change it again. Let's put 120. 120 grams. How many kilograms? 0.12. Good. 0.12. Measure the period. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.23 seconds. So that divided by 10 is the time for one cycle, so that's 0.823 seconds. Let's do 150. And let's do 170. Why are you dropping stuff? 170. So 170 grams, how many kilograms? 0.17. 1, 2, 3, 4, 5, 7, 8, 9, and 10. 9.74. That's total time. So 0.974 seconds. And we'll do one more trial. We'll go. Can I do 300? 300 might be too much. Might stretch the spring too far. Yep. We'll do 250. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11.75 or 1.175 seconds and 0.25 kilos. All right. So there, I've collected my data now. I've collected my data. Now I want to put that on a graph. If this was old school physics, you'd have to literally do this by hand. We have pivot interactives, which makes this really easy. I click on the axis, the vertical axis, and then click data column. Don't worry about the uncertainty column. We don't need to in this class. You future engineers are going to have to really deal with uncertainty in the future, but not in this class. At least not so much. The period is going to go on the vertical axis because that is the independent variable. No, that is the dependent variable. Sorry. That's the one that depends on our choice of mass. So you click done. Click on, let me zoom in, I'm sorry. Now I click on the configure horizontal axis. It lets me choose my data, the column that I want to plot the data from. So I'm going to plot the mass data. And I get this graph here. Right? It plots it automatically. Now at first glance, this might look kind of linear. What is it? It looks like it's kind of slowly curving up and to the right, right? But let's try it. Let's say it looks linear. Let's do it real quick. Yeah, quick linear. That makes it obvious that it is curving, right, as it goes over. And Kyle had the right idea. Right? Someone said a parabolic last period. Someone said could it be a parabola? Well, let's do a parabola. That looks like it fits pretty well. However, and there are ways you can like choose different graphs, and there are statistical ways to deal with or to confirm which one is actually the best fit graph. But if you know the equation for the period for a mass spring oscillator, it should give you a clue as to what is the correct way. And Kyle knows it. What is this graph? What type of graph is it?
Square root graph.
It's a square root graph. Right. And so if I pick square root graph, you'll see it fits very nicely. Square root. Very nice fit. Square root graph. Okay. Square root graphs are not linear. So if I'm going to use the process of linearization to pull information from my data set, I cannot use this graph. There are sophisticated ways to determine information based on this graph, but it's easier. It's easier to linearize the data first. So what does linearize the data look like? Again, we've done this before, but it has been a while, and it is pretty abstract concept for a lot of students, so I'm going to cover it again. And so the process of linearization like literally does what it sounds like it does. You take graphs that are nonlinear and you force them to be linear. Okay? I can't just force this to be linear just magically, right? I have to follow the rules of mathematics. So for what I like to think of, first of all, I need to get this so that it looks like, this is our equation. I need to get it so it looks like y equals mx plus b, if there's an intercept. Y and x are our variables, right? Y and x are our variables. M, for a linear graph, M is what? Constant or not constant? Constant, right? Does the slope of a line change? a straight line. Slope never changes. This is a constant. I want to write this equation in a similar way, where I'll have the vertical axis variable, which in this case is the spring period, equals some constants multiplied by the thing that varies. What varies here? Mass. However, I have mass underneath the radical. The only way to get mass out of the radical would be to square it, in which case I would end up squaring the period, right? So that tells you can't just magically get rid of the radical. So I'm actually going to put square root of mass. Okay. And then I just need to figure out what goes here, and what goes in there better be a constant, right? Even if it's multiple things combined together, better be constant.
2 pi over the square root of k.
2 pi over the square root of k. That's exactly right. How did Kyle get that? Well, he rewrote this using the properties of radicals, which you should all know at this point. 2 pi times the square root of m over k can be rewritten as 2 pi times the square root of m over the square root of k. Well, 2, is 2 a constant? Does 2 change? Not usually. Does pi change? No. Does the square root of k change?
If k is a constant, which it is.
Okay, did I change the spring?
No.
I didn't change the spring. And I didn't deform the spring permanently, so it's got the same spring constant. This is now a constant, right? So what that tells me is that I can plot the period versus the square root of the mass. What's an equivalent way of plotting the period versus the square root of the mass?
Are you just going to go the opposite way and say the period squared is equal to the mass?
Period squared versus the mass, right? If I do either of those, I end up with a linear graph, the slope of which I will be able to pull some useful information from. Okay. So you have your choice. And if this was an AP exam question, FRQ, the scoring guidelines would say the student plotted the period versus the square root of mass, or alternate solution, the student plotted the square of the period versus the mass. Okay. Either of those is fine. I'm going to go ahead and do this one. Okay. Because you can do either. That's the one that's in the equation that I've derived, so that's the one I'm going to use. And so how do I do that on Pivot Interactives? Again, by hand, you just make another data table. If you have a nice convenient piece of software that can do it, then use the software. Okay, so I'm going to go up here. I need to add a new column though, because I don't want to plot the period versus the mass anymore. I want to plot the period versus the square root of the mass. And so I'm going to put a new column in, and I want it right next to the mass, because my brain likes to see the mass and the square root of the mass right next to each other. You don't need to, because when you look at the graph, you can choose whichever column you want to plot. But I'm going to go ahead and put it to the left of this guy, so I just click on the ... insert column left. So now I got a new column. Now, to my knowledge, there's no way of putting an actual square root symbol in the boxes there. So I'm just going to type SQRT, parentheses, mass. That's what is going to be in this column. The units for the square root of mass are the square root of kilograms. It sounds weird, but when you take the square root of mass, the units that you measure that in are the square root of kilograms, just like kilograms squared, right? But the other direction.
You do it as an exponent fraction?
What's that?
You do it as an exponent fraction?
No, you don't need to here.
But instead of saying square root of mass, can you say mass to the 1/2?
You could, but then you'd have to use the little caret symbol. So it's Again, the variable then is going to be the square root of m. Right? Okay. Now, for those future engineers in here, spreadsheet software, and really scientists in general, but a lot more people become engineers than scientists. Spreadsheet software is crucial. It will be crucial to your job. I know there's a push for Google Sheets because Google is taking over everything. However, in my experience, I know it's gotten better, but in my experience, Excel, the features of Excel, Microsoft Excel far exceed the capabilities of Google Sheets. And then once you get to college and once you go into the profession, you'll start learning things like MATLAB and other very much more sophisticated programs that do a lot more than just spreadsheet operations. But spreadsheet software is incredibly powerful. If you were doing this by hand, you'd have to make a new table, which on the AP exam, if you have this as a question, you're going to have to do. You're going to have to fill in data into a new table. But in this case, I would just take 0.05, take the square root of that, put that number here, right? Take 0.09, take the square root of that, put that number here. But spreadsheet software and Pivot Interactives allows you to do that all at once. So I'm going to change the column formula. Notice I have one of the column names here. It's mass. And so all I need to do is go down, hit that square root button, and then choose mass, close the parentheses. Now I have a formula that's going to take the input here and then take its square root and put that there. Now, if you wanted to do something with the period, you just have to insert the new column to the right of the period. And then you'd be able to say the period squared if you wanted to do it that way. But since we're doing it this way, I got the square root of mass. I hit submit. Those data are already there. Okay, so it does the calculation for you. All right, and now I can go down to here, and instead of plotting the period versus the mass, I can plot the period versus the square root of mass. And when I do that, the square root curve fit does not work anymore, obviously. But what does it look like this data looks like? What relationship does it look like exists between these data? Linear. You can pick proportional or linear, as you'll see. They're very, very similar. Right? Yeah, we'll just pick one. Let's pick proportional. Let's pick proportional. Then we don't have to really deal with too much with the intercept. Okay. And the 0, 0 is a valid data point, right? 0, 0. So you could use that. So, yeah. Let me actually look. No, that's pretty good. That's pretty good. So now, obviously, this is linear. And we did this for a reason. We did this because of this slope. This particular slope tells us something important. Okay. Oh, wait, first. Where can I get the information for that slope? Right down here. Right? I have t, which is a period. It uses the inputs, the things that I put in the data table. T equals a times the square root of mass. T equals a times the square root of mass. Right? That's the equation right there. And then it gives me the value for a. It gives me the value for a. That's where I get the data. And the units, seconds over the square root of kilograms, that will make sense if you think about it. But what I can do then is say, all right, I've analyzed the graph. I've determined the slope of my linearized graph. And I've read the graph. If this was by hand, you would have to measure it, the rise over run, determine the slope. But here, I just look down here. A equals 2.36 seconds divided by square root of kilograms. That's the units. Okay. If you work out the spring constant, K, it's kilograms times meters per second squared. If you take the square root of that, it's in the denominator, so it gets flipped. These are the units that you end up with. Seconds over the square roots of kilograms. Okay. If you tie it in with... Yeah. So what I can do here now, I have a numerical value for the slope of this line, which I now know is exactly equivalent to 2 pi over the square root of k. I can set this number equal to this expression here. Right? A, I know, is going to be 2 pi over the square root of k. And I can solve this for k now. So this is an experiment that I can use to determine the spring constant for that particular spring. You all see that? So if I solve this for k, multiply both sides by the square root of k, divide both sides by a, I get the square root of k is 2 pi divided by a. Square both sides. I don't know why I'm doing red. K then, spring constant, would be 4 pi squared divided by 2.3. Actually, let me just do 2 pi because I'm putting this in the calculator. Divided by 2.36 squared.
7.0.
7.1. 7.1. Spring constant units, newtons per meter. Right? Newtons per meter is the unit for this guy. If I was to take the square root of those units and then invert them because it's in the denominator, I get seconds over square root of kilograms. So it makes sense. Newton is kilograms times meters per second squared. So the meters actually cancel out. I end up with a kilogram that's not squared, so it stays under the radical. But I end up with a second squared, which is why this guy isn't under square root. What do you think that the manufacturer, like we buy these spring sets from a manufacturer. I have it here. This is one of those spring sets. Did I get all that in the video? Hope so. So there's a bunch of different springs, different spring constants, different lengths. What do you think the spring constant is rated at by the manufacturer when we bought that spring constant? 7 newtons per meter, right? Plus or minus probably 1, or plus or minus 0.1 or 0.05, something like that. So yeah, it's a good experiment. This is a much better experiment, but than just hanging one single mass and doing mg equals kx, right? That is a way to get a good approximation in reality for a spring constant, but when you can get multiple data points in an experiment like this, it's much better, much better. Okay, so I'll leave it at that. The experiment that you're going to do, you will have to linearize, like I did today, one of the equations. And I'll give you a heads up. This should, for you good physicers out there, this should help you decide which graph you might have to linearize. I want to see all three, though. I want to see valid data points. I want to see the graphs for all of them. But the equation for the period of a pendulum, and it's no accident that it looks like this, because the way that we actually theoretically derive the expression for a period of a pendulum is the same physics, same type of physics that we use to derive the equation for the period of a mass spring oscillator. That's why they look similar. It's 2 pi. Again, any equation you see pi in, there's a circle there somewhere. It's hidden. It might not be a circle in physical reality, but there's some manifestation of the physics that you can plot on a graph and make a circle. That's why that pi is there. Times the square root of not m over k, because we're not dealing with a spring. We're dealing with a pendulum of length L, and that gets divided by our good friend, little g. So if you ever want to know what the value of g is on another planet, if you get stranded on another planet, you can just set up a pendulum, measure the period, measure the length, determine the value of g on that planet. Okay. You good physicers here, this should give you a clue as to what your results should be. But I want you to confirm those results, or confirm your ideas by actually doing the experiments. Okay. All right. And if you look, right, the graph itself is 10 points. Graph and data table, 10 points. Describe your experimental design here. Include what quantities did you hold constant, which did you vary, which will you measure, which did you measure. Then describe your results. Which quantities did you plot on the axes? How did you linearize the data, parentheses, if needed. If not needed, you don't need to. The meaning of the slope and intercepts for your line. A statement of the relationship variable A is proportional to variable B. Okay. Yeah, for this one, I want complete sentences. I don't want just blurbs, just quick blurbs, because it was hard to read some of the last one. The last lab is a little too low level. We need to start bringing it up a notch. Okay, yes, sir.
You say complete sentences, but are we allowed to use like bullet points to address each one?
Yes.
Okay.
Yes.
That's what I did last time.
But I had AP students starting sentences with lowercase letters. That was like, and not just a few. Terrible grammar, no punctuation, no periods at the end. Come on, guys. Come on. You are beyond that level at this point. At least you should be. Yeah. Okay. Last thing I want to point out, because we talked about this last period. You guys heard of atomic clocks? Atomic clocks. That's how we keep time. Like our clocks here, our watches, we always set them according to something else. Well, what's the standardized time? The standard time is kept with atomic clocks. This watch here is a pretty good watch. It's going to lose a second, maybe every couple months or something like that. Your best grandfather clocks will lose a second after maybe several months or a year. Atomic clocks, lose a second after like 10 million years or something like that. How do they work? They use vibrations of cesium atoms that emit radiation because accelerating charges emit radiation. And the vibration frequency, we know to a certain degree, a high degree of certainty, and those vibrations are literally simple harmonic oscillators. So yeah, we're dealing with things on the ends of springs, we're dealing with pendulums, but you take this stuff, the basic physics that we're learning now applies to, I can't overemphasize how many different areas of physics and engineering simple harmonic motion concepts apply to. So just remember that when you're talking about just the pendulum swinging back and forth. Okay, there's a lot more to it, You want to study wave motion, wave mechanics, you want to do anything with modern physics, quantum mechanics, it's all about waves. It's all about wave mechanics. Okay? And simple harmonic motion is where that starts. And that is my spiel for today.